Alright, so the first three problems from last weekly contest. Let's start with the third problem. Right, so let me clear this. Sum of k subarrays with length at least m. So we are given an array nums and two integers k and m, and we are told that we need to find the maximum sum of k non-overlapping subarrays. So there must be k non-overlapping subarrays, and each of the subarray must be of at least m length, right? So we can choose if m is 2 and k is 2, then this can be one subarray and this can be another subarray. Eventually, we get the maximum answer. Similarly, if we don't have anything, then we can select select all of them. We get -10. We have to select all of them actually in this case because we don't have any other choice. We'll always have a valid answer because k is fixed in the constraint such that we have an answer always. And that's it. That's the problem. This straight away leads to the DP solution. Well, what will be the state is the question, since we are talking about top-down approach. So states, suppose we have something like this: D, E, F, G, H, I, J, K. All right, and we have, suppose, k as 3 and m as 3, right? Then we have to decide three borders, and those three borders can be anywhere. Suppose I starting from here can be something like this, right? So this will end here. The next j can start from here instead of here. Suppose this was negative, so we can skip elements as well. And this, suppose, started from here, right? This was the only way. If we had multiple elements, then there must be, or there will be more choices, right? So we can skip elements, we can start from any other element, and we can end at m or more, right? So there can be decisions. First decision will be skip element. So I don't have anything concrete yet, but just I'm writing down the decisions so that I can eventually get to the concrete choices. So I need to skip element. I can end element. By end element, I mean creating a border so that I double down on a subarray, right? And then I can continue extending the element or the window or finally I guess we need to start somewhere, right? I have not even started, so start subarray. I guess these are the four choices that we can have. Let's talk about the state. So we have our index for sure. We need an index. We need a k. So we have a k, right? So we need to know how many subarrays are yet to be filled or chosen. So k is needed. And finally, if we can continue, right? If we can continue or if we cannot continue, right? That should be the case. Why is this the state? That's because we can have at least m length, so we can have much more than m length, right? So when we decide on a array, we straight away take m elements into account, or take sum of m elements into account. And how are we going to do that? We can iterate over the m elements. M is just 3, but what we can do is, to make it more efficient, we can have a prefix sum. Using prefix sum, so not just nums, we are going to pass the prefix sum as well to the recursive function. We need to pass the index as a state, k as a state, and can continue as a state. So when we start, we are going to straight away take into account the sum of m elements using the prefix sum, and then we continue. We are going to add the nums of index contribution to the already calculated sum, right? So we can have, suppose, more than m elements by this point of time. So I don't want to write contribution of, let me write it as already calculated sum of elements for this subarray, right? This will get more clear as I write the code. And end element and skip element is straightforward. Let's discuss on what will be the state values here. Since we are skipping the element, we have index that will increment, we have k that will stay as it is, and can continue will be initially false when we are skipping the element, right? Because it's not that we have started on a subarray, so can continue will remain false. We can't continue because we don't have a subarray, right? That's why it's false. For end element, the next state transition will be index end element, right? So we are ending the element there, ending the subarray. So this can increment the index or may not increment the index. That depends on the state transition of the other decisions, right? So let's say that we are going to increment the index. We are going to reduce the subarray because we have decided upon a subarray, and we can not continue now. Since we have ended the element, we need to start fresh, right? So this will change to false. All right, and lastly, yeah, I guess this is it. And this one is straightforward. Since we are continuing, let me separate this a bit. Let's do this state transition first. Since we are starting a subarray, and we're straight away taking m elements into account, right? So we are going to add, first of all, the sum that we can calculate using prefix sum, and the next state transition will be index plus m this time because we are jumping the m elements. K will be, you know what, we will reduce the k right here because we have decided upon a subarray. We have not ended it yet, but we have decided upon a subarray, the starting part of it at least. So instead of ending element, we are not going to reduce the subarray, so we are not going to increment the index as well, right? This can be confusing. We can do that here or we can do that here. I'm doing it here, that's why I'm not doing it here, right? So this is the state transition for this one. decision, this one is continuing or continue to extend the subarray window. That means we are adding the nums of index, and the next state transition will be index plus 1, since we are only processing one element at a time in this decision. And lastly, we have not reduced the subarray since we have not ended it yet, and we can continue this time. So we can continue. My bad, I forgot this state. So can continue will be staying true here. So we have started on a subarray. We are continuing on a subarray. So both the can continue for both the decisions will be 1. And yeah, this one is this one is this. So we are good. We have the concrete state transitions for every decision, and we can start without the memoization first and then with memoization. So we are going to have nums prefix that we are going to calculate it here. Size will be initially 1, and as I iterate, I am going to push back the elements plus n. This will give me the prefix. Now the next state is index will be initially 0, k will be initially k, and can continue will be initially 0, since we can't continue because we have not started it yet. Lastly, let's start with the solve function. This should be prefix. These are passed by reference. Index, this is k, and lastly this is can continue. So if, what will be the base case? Base case will be if index is greater than equal to nums dot size, right? So we have surpassed and exhausted nums. In that case, we can return either we can return 0 if k has also been exhausted, or we can return something very negative value, because since we are maximizing, so we are going to have in the recursive function the answer that will be initially int minimum, and since we are maximizing and we don't want to disturb our answer, that's why we are going to send a very minimum answer to avoid that flow to disturb our answer, right? So in that case, my base case will be something like this: return if k is equal to 0. That means we have gotten the answer. So we have the required number of subarrays of uh, corresponding lengths that we want. So we can return 0 here. Otherwise, we can return something very negative. If I return int minimum, it's going to overflow. So I can return something very negative, but not really that makes it overflow. So what I can do is minus 10 to the power 4, and these 3 zeros will make it 2 to the power 7. So I can return something like negative 1e8, right? And hope that it won't overflow. If it does, then we need to change this value to something less negative, right? Probably 10 power 7. So like we said, we are going to have an answer. This will be initially int minimum, and if can continue, let me copy this. Answer is equal. So we have decisions, right? So at this point we can continue. Else we can't. So here in the can continue section, this means that we have started the subarray with at least m sum or m elements accounted in the sum. I said at least, so it can be more as well in the sum, right? So the two choices here will be what? We can keep continuing one by one each element and add its contribution to the sum, or let's do this first. So I will have an answer which we are minimizing or maximizing, and we are adding nums of index contribution. Since we are adding one by one contribution of each element, nums and prefix will stay same, index will increment, k will stay same, we have not ended it yet, and can continue will stay same, right? The next thing is we can stop here, we can stop right here, end it, right? That means we can have answer nums of, sorry, nothing will be contributed this time, nums and prefix will stay same, index will stay same, right? I just mentioned that index will stay same. Why? Because we will be incrementing the uh, index in the continuous section itself, so we are ending it here, so that means nums of index has not been processed yet, it will be processed as part of the next recursive call. So nums of index will stay as it is. We have uh, not, you know, going to reduce the subarray because that has already been done in the else section when we started the subarray, right? So that will be more clear as I write the else part. So k will be k and can continue this time will be 0 because we have not started it yet. We have ended it. End the subarray. Lastly, here the two choices will be started because we have not started yet or the subarray yet. So started means answer is equal to max of answer comma prefix of index plus m minus prefix of index of the first m elements, right? Alright, so nums will be nums, in prefix will be prefix, index will jump to or jump by m elements, k will reduce right here, so this should clear some doubts of why didn't we reduce the k here, because we have already done it here, right? And lastly, can continue will now change to 1, right? So that's it. We have some edge case here because we must have at least, we don't want to go out of bound here, right? So we must have the condition here, that means we must have at least m elements after index, right? So nums dot size minus index is the remaining number of elements, and this should be greater than equal to m, at least m should be there, otherwise I can't perform this particular call. And the next choice that we have after this is we can skip, we can end, we can keep continuing, we can start. So since we have started it, we can end it again, end it right here. What does it mean? We have not started the subarray yet, but we can end it here. So this can be confusing at first. Oh, I'm sorry. I'm sorry. I am using the wrong word. This should be skip. Skip it. So we can skip it. We can end it. These two are already performed. Right here, right here. So skipping is straightforward. We can maximize the answer. Solve will stay solve. Nums prefix as it is. Index plus 1. K will remain as it is. And 0. Right? We can return the answer here. Let's see if this works. I'm sorry, we need to pass M as well. Since M is not changing, I can pass it by reference. Doesn't make a difference, but still. I'm sorry, it should be here and here and here. Lastly here. Let's see now. There should be a comma. We need to memorize it. Okay, I guess something is not right. This should be also comma. But if this works, we need to memorize it. What we can do is we can have a cache. Mind that the time complexity or the constraints are a little bit strict. The runtime is very strict for this problem. So taking vector of what 3D vector, because we have three things, three states. This will be of O of n. K will be in worst case n by m. So if m is 1, then k will be n. So n and can contain 0 or 1, so it's 2. So n square, 2n square will be the time complexity, and we need to memorize it, so we can have 2n square. But if we use a 3D vector, then it's going to give us a TLE or a MLE, I don't know. So we can have something like this using this structure, so it's not going to take up much space. I mean, in terms of time complexity, it's not going to TLE. So this can have a cache. I'm sorry, this is the wrong notation. This is n, so let me take 2001. This should be 2. Initially the values will be -1, and here I'll check if cache of index k and can continue is not equal to -1. Return the cache and keep updating always. Let's see now if this works out. Okay. Yes, we need to increment the place once. Now let's see. And why this is taking too long? Let me refresh it. This works. Okay, so let me see where it is going bad. This is going negative. Oh my god. I guess I missed the part where at this point k is going negative, right? So k should not get negative, otherwise we should return this. But we need to take care of that somewhere here. So if we have can continue, that means we have a subarray that is already started and not ended yet. And if we have ended it, it must start the else condition. So before checking or before continuing or starting a new subarray, we should check if k is still 0, or if k is 0, then we don't need to start the new subarray. That's why k was going negative, right? So we can return 0 here. Otherwise, it's going to start a new subarray and keep continuing, right? Let's see now. Time complexity, space complexity will be same based on these three states. And this is a very bad time complexity. We can use or convert this into a bottom-up approach. That would be much better. So let's move to the first two problems. These two are straightforward. First one, find the largest almost missing integer. We are given an integer array nums and an integer k. It's almost missing if x appears in exactly one subarray of size k within nums. So what we can do is we can start a sliding window, and suppose we have something like right. Suppose k is equal to 3 or 4, and we take this. So we have a map which keep track of how many elements are there in a window, and if we have a window that is of size k, that is this one, in that case we traverse the map, and basically what we want is if x appears exactly in one subarray of size k within nums, then x is almost missing. That's the definition, and this is the validity. So return the largest almost missing integer from nums. If no such integer exists, return -1. So what we can do is we can have a global map first of all. Global map will keep count of every number that appears in array keep track of every number that appears in array and how many times it appears in a k-sized subarray, right? So by the end we can just iterate this global map and check which are the ones that appears only once, and among them what's the maximum. So we can have a answer that keeps on updating as we traverse the global map. So this is straightforward, and map will keep updating. This map will contain every k size window, number occurrences, and every time we hit the k window, we are going to use the map, traverse it, and update the global map. Okay, so straightforward. So if we do a dry run, this then we have a I, J, keep updating the map, keep updating the map, keep updating the map. At this point, we hit the k size window, traverse the map, update the global map, move forward the window. Now, since all of the other sub-arrays will be of size k, keep traversing, keep updating the global map, and by the end, by the end, traverse the global map and update the answer, right? So we can have a I, J, and order map. Also, by the way, there can be some edge cases. Let's discuss that as well. Suppose something like 0, 0, and suppose k is equal to 2, right? In this case, what should be the answer? This is the window that we are talking about, and we are going to count 0 appearing in only one sub-array, right? It is appearing twice, but we want x appearing exactly one sub-array to be count as a almost missing element. So here 0 is almost missing because we have one window of size k and 0 appears only in that one sub-array. There is no other sub-array. Right? Even though count is 0 or 2, it doesn't matter. It appears only in one sub-array. That's all matters. So we are going to have a global count. So I'll reduce the k and I'll keep updating the map. So I'm just growing the window to the point where it reaches a k size window, and then I'll start another loop, and this will continue as long as j is less than nums.size. Alright, and since all the throughout this loop, every time we increment I and j, the window will be of size k. So what every time we need to do is traverse the map. So at this point, window is of size k, traverse the map, get the number, get the count, get the map. We don't really need the count, by the way, because no matter how many times it appears, it doesn't matter, right? So technically, we don't even need this. We can just have a set as well, right? St.insert nums of g. So yeah, so at this point, let me get the set, and we are going to increment the global count or global map. That will be num. I'll increment it by 1 because it appeared only in this sub-array. So every time it appears in a k size sub-array, I'll increment it by 1. And now I'll increment I. So st dot oh my bad, I forgot about that. Since uh, having a window, that's a sliding window, right? We do need to keep count because we are going to lose and gain certain elements, and that can be the same element. So we are going to need a count for sure. I'm sorry, I just realized that. So I'm changing this back. Alright, this should be map, this should be count, and that's it. So I am incrementing I. Before that, I am basically reducing the map count, and if map count it's a good practice to erase the number as well from the map. Otherwise, there can be zero values, sometimes even negative values as a count. So that should not be the case. And then increment j. Before that, update the map. Right. So these two lines are straightforward. The only thing is there is one edge case here, and that is the last subarray will not be counted because I'm counting it here. Before that, it will go out of bound. So we need to take care of that. By that, I'll do this. So the one last time I will do this, but before that and after that, I'll break out if j is equal to num size. Okay. Lastly, we can traverse the answer. Traverse the global map and get the answer. So for that, I will have a number and a count from the global map. If the count is equal to 1, I will add that to the answer if it is a maximum and return that as my answer. Let's see if this works. It does. Let's submit it. Time complexity will be O of n, space complexity will be O of n. That's it. Let's move to the second question. Let me just, longest palindromic subsequence after at most k operations. We are given a string s, integer k. In one operation, we can replace the character at any position with the next or previous character. And this is wrapped, so it's a cycle. A becomes z if we go backwards, and z becomes a if we go forward. And we need to return the longest palindromic subsequence of S that can be obtained after performing at most k operations. Initially, it might look like something greedy, but it is not. It gives a lot of hints towards, it being a DP. So I can just take an example and can something like this. So I'll start from here, right? What are going to be the states of the DP is what is a question that should be answered first. But before that, let's do a simple trial on how are we going to solve it. We want the maximum longest palindromic subsequence, so that gives us a hint towards we can skip elements, right? We can skip elements, we can start from anywhere. So what I'm going to do is I'm going to try get the maximum length as the answer, right? Starting from here, I try to get the maximum as the answer. For that, I will see it takes a minus k operations, whatever um, we can minimize the difference in terms of how are we going to take it. Let me bring the pen now. So basically, uh, if we have an alphabet here, this is a cycle, right? And this is another alphabet. Suppose this is A and this is K, right? So that means we should, I'm actually, this is A and this is K, right? So we can take this, we should take this, and we should avoid taking this. That is straightforward. What we can do is we can have something like s of I minus s of j, take the absolute difference, right? And this difference can be taken into a variable, and we can take either this difference or 26 minus difference, right? This will take whatever the minimum path will be between these two, right? So I will check that, get the operation inside my a state. So we need a state for that, right? uh, yeah, so we have at most k operations, right? So we need a state that we can have initially k operations, and then we'll keep reducing the operations as we do this thing. And then if this does not go negative, then we move forward and we do the same thing. In the meantime, we can also skip elements. Suppose I skip I or I skip j, right? So that's another possibility. And like I said, we have k as a state, we have I and j as a state, and that's all I need as a state, right? So there can be a couple of base cases. You know what, let's not waste much time and let's start coding it up and then see what all decisions and transitions that we need. Again, we need to memorize it. We are going to keep it for the last. And this is the first state, this is I, this is j. J will be initially the last element, right? I hope s dot length gives integer, otherwise I'll typecast it. So sort function string, passing it with a reference. This is important actually. It was giving me memory limit exceed for some reason without this. I mean, for some reason I know the reason, but yeah, it was a little bit challenging to figure out the bug. I and j are the three states, k, I, j. Firstly, k should not be negative, right? That can be the first base case. If k is negative, in that case, that means uh, we have exhausted all the operations. We have actually gone beyond it. Since we are maximizing, we should return something minimum. Let's return int minimum. The next base case will be what if I and j has surpassed, right? Suppose there were some elements and then b and c and then some elements, and I is here, j is here, right? They can be a even length palindrome, right? Even length palindrome. In that case, I and j will be ending up here, suppose, and then we do that operation that we do, right, of checking, and then we move forward. I and j got swapped, right? That means I is greater than j. The equal case, I will handle it in a separate base case. So in this case, we need to return 0. That means we have exhausted everything. We are not going to return any length because we have no length to return. What if we ended up something like this, a odd length palindrome, right? I is at I is at the same place, j is at the same place. In that case, we need to return this length, right? The other lengths are being processed within the recursive function that I will write, right? The recursive line where we call the solve function. There we are going to add the 2 that is going to be I and j length, right? I as a number or alphabet, j as an alphabet that contributes 2 to the length that we need to calculate, right? But here, since this is the base case, we need to return 1 here. So if I is equal to j, return 1. And lastly, what if I is exhaustive, right? J can also exhaust, but we can just have one base case for I or j. Let's consider I. If I is exhausted greater than equal to s dot length, in that case also return int minimum, because at this point means k has not been exhausted, right? K yeah, I guess we don't even need this base case actually, if I'm not wrong. Let's think about it, because we are going to have ing already taken care of. I guess we are good, so we don't need this. Let's remove this. Next thing is the answer will have an initial value of 1, because we can have at least one character in our length, and that character alone will be a palindrome. So this is the answer. The next thing is we are going to check if s of I and s of j are equal, right? If it is equal, then the difference will be 0. So I'll end up doing that. So I don't even need to check that. I can just get the difference, right? S of I minus s of j, like we did. ABS and operation is what we need to count. Minimum of difference, or the other way difference, 26 minus difference, whatever that is the minimum. If they are equal, then difference will be 0, operations will be 0. So I will maximize the answer by adding operation plus, sorry, not operation. S of I and S of j will be counted now as part of the palindromic subsequence. So I'll add 2 to the length and call the recursive function pass s. K will be reduced by this many operations. I will increment by 1, j will decrement by 1, right? Now we can skip I or we can skip j. So I can have a max of answer. I can skip I, that means I will have I and j, s, k, ij. So I can skip I can keep I as it is and skip j. Sorry, j should be -1. Right? This is it. These are the three conditions or three decisions, and we can return the answer here. And let's hope for the best. Let's see if this works. It does. Let's minimize it. Let's have a cache. This will be a 3D cache. N plus 1, or actually let's have k as the first state, and then a vector of int. Let me copy it, and then n plus 1, because ing will be n plus 1. Initially the value will be -1, and I'll check if cache of k, I and j is not equal to -1. In that case, return this and keep updating. Let's see now. Time complexity will be, I guess, O of kn square, and actually we can try to further optimize by pruning some test cases, or pruning some calls to the recursive function here. Since we are going to have uh, some answer here, if that answer, if the remaining elements, what are the remaining elements? J minus I plus 1 are the remaining elements. If that is a length that is going to be smaller than answer or greater than answer, only then do a recursive call. Otherwise don't do this recursive call, because I have a better answer already. So it might prune some cases, and the same goes for this particular call as well. And let's see now. But I don't know if this really helps out. I guess it does. But that's the problem. Time complexity will be O of n square k. Space complexity will be O of n square k. I guess k is equivalent to n, so technically O of n cube in terms of time and space. That's the third problem. Thanks.